right, well, sugar cookies up here if anyone, the snack, happy National Sugar Cookie Day, everyone. So, couple of quick remarks and then we'll hand the floor over to Mitch here. So, I just wanted to start out by saying that Mitch grew up on sunny tropical beaches and learned to scuba dive with certifications as a rescue diver, nitrox, and emergency oxygen provider. I'm not sure if everyone knows, but these sunny tropical beaches happen to be in Missouri, about as far away from the coast as you can get. But Mitch now has a marine research experience and diving experience all over the world, including here, Florida and Galapagos, to name a few. While at UNCW pursuing his master's in marine science, Mitch also earned a post-baccalaureate certificate in geographic information science and a certificate from the highly competitive Cornell Ocean Color Satellite Oceanography course, all also serving as a research assistant in our team and interning and staying busy with lots of other things. So Mitch could now use these GIS skills to determine that he grew up about as far away from the coast as is physically possible. But we're really delighted that you landed out here on the coast and in particular in the Coast Lab. He's been a wonderful lab mate, always bringing ample doses of friendliness and curiosity to our group. We'll hear one piece of his Wilmington story here during Mitch's thesis defense. And just to set some ground rules here quickly, we will first hear a roughly 45 or so minute presentation from Mitch. We'll have a little time for questions from the full audience, and then I'll kick the general audience out of the room and off of Zoom, and we will have a private committee defense. So with that, Mitch, the floor is yours. Take it away when you're ready.
Awesome. Well, thank you for that very awesome introduction, Phil. So yeah, my name is Mitch Torkelson. And this is my thesis presentation titled Integrating In-Situ Measurements and Satellite Imagery for Coastal Biogeochemical Analysis in the Cape Fear River Estuary. And my thesis committee includes Dr. Brezahan, who is my principal investigator, and Dr. Halls and Dr. Liu. And this research would not have been possible without each one of them. So I appreciate your guys' help in assisting me with this. So I'm going to start by giving some background information about coastal ecosystems. Now, these ecosystems have intrinsic value and natural capital, and they're worth monitoring. For starters, they offer critical nursery grounds and habitats for a plethora of species. Locally, these include eastern oyster, flounder, migratory birds, and blue crab, just to name a few. They also offer shoreline protection. The vegetation types that are found here, like mangrove forests, salt marshes, and seagrass beds, help to prevent coastal erosion with their intricate root networks, as well as to buffer wave action and storm surges to protect coastal infrastructure. And all things told, these ecosystems contribute $2.5 trillion annually to the global economy. And this figure is the equivalent of the GDP of the 7th largest country's economy in the world. And so they're very important. And to monitor these ecosystems, there's a lot of methods that work and that are in use, but one of which that we'll talk a lot about today is remote sensing. And ocean color remote sensing is a subfield of this, of remote sensing, which harnesses the electromagnetic radiation from the sun, which travels through space at the speed of light, and interacts with all of the particles and the aerosols in the atmosphere, as well as the materials found on Earth. And each one of these materials that it interacts with has its own spectral signature, which means that it interacts with different and unique wavelengths in the electromagnetic spectrum. So it's kind of like the material's fingerprint. And you can use these fingerprints to help identify what you're looking at in a satellite image. And one of these materials that we'll be talking a lot about today is phytoplankton. Now, phytoplankton are these teeny tiny microscopic organisms that live in the ocean, whose primary pigment is chlorophyll A. And chlorophyll A, as we can see here by its spectral signature, absorbs light in the blue and the red wavelengths and reflects in the green and the near infrared. Now, our naked eyes can't see near infrared, but we can see green. And so as the concentration of chlorophyll A increases in the water column, so does the ocean's green hue. And so algorithms have been developed to relate the ocean's color to the amount of chlorophyll that is found inside the water column. And though chlorophyll A is not a direct measurement of phytoplankton biomass, it's been seen to be a reliable indicator of. And one of the more commonly used algorithms to do this estimation of chlorophyll A is the OC4 algorithm. This is the algorithm that NASA's Ocean Biology Processing Group uses to process all of its ocean color remote sensing missions, as well as some of the European Space Agency's missions as well. And it utilizes 4 wavelengths of the electromagnetic spectrum, and it harnesses the reflectance signal coming from these 4 locations in a 4th order polynomial equation. And it does this to maximize reflectance ratio between blue and green visible light bands. And it's the main goal is to estimate chlorophyll A concentration. And I use the word attempts to do this very carefully because it's not a perfect science. As we can see here, this is a comparison between all of these in situ measurements, as you can see here with the black asterisks, and the chlorophyll A estimation from the satellite sensor in space. And so for the most part, they follow the same general trend. However, if you were taking one of these in situ measurements, let's say this one right here, you can see that there's going to be about a whole order of magnitude difference between what you're seeing in your sample and what the satellite is seeing. So it kind of generalizes what the chlorophyll A concentration is doing in that region. So if you're looking at any particular in situ measurement, there's going to be a high degree of variability between what you're seeing and what the satellite is seeing. And this effect is exacerbated even further if you're doing this type of science in a coastal ecosystem, because there are characteristics in the coastal ecosystem that just aren't present in the open ocean. For starters, this includes complex optical properties of the water column, a lot more suspended sediment found here being stirred up from river discharge, as well as sediment resuspension events from like wave action, as well as there's a lot of color dissolved organic matter here, and there's more species of phytoplankton found here as well. And you can also have a lot more atmospheric interferences coming from this region, where you can have aerosols and gas being emitted from infrastructure on the land, and you can have photon reflection bouncing off of adjacent land masses as well, which interferes with your water leaving signal that you're measuring with the satellite. These regions are a lot more spatially variable. You're going to have rapid changes of turbidity and phytoplankton here, and these are also tidally influenced regions. And the satellite may just generalize this entire thing instead of catching all of these intricacies that you can observe with your naked eye or with an in situ measurement. And you also can run into shallow bottom effects. The coastal ocean is just inherently more shallow than the open ocean. And so if a significant portion of that light is penetrating all the way through the water column and scattering off a particularly reflective surface like sand, this can serve to interfere with your satellite signal as well. And so all of these factors kind of contribute to the overall requirement of having tailored tools and methods for conducting ocean color remote sensing, specifically in the coastal ecosystem. Which brings me to the Seahawk Hawkeye CubeSat mission. Now, this mission was launched in 2018. It's a UNCW CubeSat mission, which it collaborated with NASA in order to produce and to launch. And it was launched on the SpaceX Falcon 9 mission with 64 other CubeSats. It kind of was just a big carpool to space, if you will, for CubeSat missions. And the design and inspiration for the construction came from the Sea-Star and SeaWIS mission, which was launched in 1997, but was decommissioned in 2010. But Seahawk has a lot of advancements with regard to its predecessor, the Sea-Star. So for starters, it was made with off-the-shelf components, which brought the development time down to a rapid 2 years time, and it required just $4 million. It's about the size of a shoebox and weighs just 3 kilograms. In contrast with the Sea-Star mission, which took about a decade to make and cost $100 million, and it's much, much bigger. You can see the size comparison here, with Sea-Star being about the size of that human being, and then Seahawk, if you really squint your eyes, you can see it's about the size of that guy's shin. So it's about 200 times smaller and 100 times lighter than a Sea-Star. Now, the Hawkeye is the sensor that sits within the Seahawk frame. Now, the Hawkeye is just about the size of a Rubik's Cube and features 4 linear arrays and measures light at 8 spectral bands. And a band is just a window of the electromagnetic spectrum that the sensor is taking measurements in. So it's a range of wavelengths. And it captures 15 baseline scenes per day, each of which have the dimensions of 200 kilometers by 600 kilometers. So it's a nice long strip And you can see an example of what the Hawkeye imagery looks like here, where we can see the Chesapeake Bay, the Outer Banks, and down here is Wilmington. And it has really high resolution, which is one of its main advancements from the CWIF sensor. The Hawkeye captures its imagery with 120 meters per pixel, with comparison to the much more grainier imagery of the CWIS, which was 1100 meters per pixel. And so this means you can fit 84 Hawkeye pixels within the space of one CWIS pixel. So you can capture a lot more of those finer details that I was talking about that exist in the coastal ecosystem. So to finish setting the stage, really, we've learned that coastal ecosystems are worth monitoring because they are critical for biodiversity. They contribute a lot to our economy, and they also help to protect the shorelines. And we can do this quite effectively with remote sensing because it offers large-scale observations over time, passively. However, there are some limitations with using remote sensing methodology. You're only capturing that surface level characteristics of the water column. You're missing all that subsurface dynamics. And they're also weather dependent. So if you have a storm surge, or if you have a storm roll in, or fog or cloud coverage, it's going to render a lot of this satellite imagery useless. However, if you were able to augment this satellite imagery with in-situ measurements, you would be able to capture all of those three-dimensional water column characteristics, and you would have some in-situ measurements to ground truth what the satellite is seeing. And this approach, by integrating these two data sets, is a good method for getting the most complete coverage of the water column. And so our research objective is to integrate satellite sensors like the Hawkeye with in-situ sampling to have a more complete understanding of the Cape Fear coastal region. And in doing so, we hope to answer 3 research questions. The first of which being, how can the integration of in-situ measurements with satellite imagery enhance our understanding of the temporal variations in water quality parameters in the Cape Fear River estuary? Question 2 is, how do specific satellite sensors perform in observing physical and biological parameters in coastal regions? And then what are the discrepancies that exist between these in-situ measurements and our satellite-derived measurements? And if the discrepancies exist, what factors are contributing to them? So here's a summary of those points. And we're going to answer these questions by first collecting in-situ data, and then we're going to go back and look at synchronized imagery from satellites. We're going to use these data sources to run a water quality evaluation of the Cape Fear coastal region. And then afterwards, we're going to do a matchup analysis where we compare these 2 data sources and quantify any discrepancies. And so our research took place in the Cape Fear River estuary in southeastern North Carolina. This estuary is impacted by surface water or nutrient-rich surface water runoff from upstream concentrated animal feeding operations, as well as dense urban settlements like Fayetteville, Durham, Chapel Hill, as well as Wilmington. And all of this surface water runoff collects into the estuary, whose water flows down and eventually collects into the 35-mile long Cape Fear River, which courses southeastward and past Wilmington and eventually empties into the Intercoastal Waterway, as well as the Atlantic Ocean. And so our first data collection day took place on May 3rd, where we took the RV Cape Fear, as seen here, from the CMS dock down the Intercoastal Waterway through Snows Cut and up the Cape Fear River, and ran a technical evaluation on the Acrobat instrument, which I'll talk a little bit more about on the next slide. But we just wanted to make sure we were comfortable with using the Acrobat and making sure that it was working properly. So our main data collection day came 2 days later on May 5th, where we ran these 7 transects here. We took the RV Cape Fear up the Intercoastal Waterway and out the Masonboro Inlet, which you can see here. It's a 300 meter long inlet, or wide inlet, which is straddled by 2 rock jetties, separating the Masonboro Island Reserve from Wrightsville Beach. And it's a unique point of exchange between the material in the Atlantic Ocean as well as the Intercoastal Waterway, because it's very tidally influenced. And so these transects here are about 4.5 kilometers in length, and the first one being about 2.5 kilometers from the mouth, and the last one being about 4.5 kilometers. And these transects we placed them in this region to hopefully observe the changes that happen between a tidal cycle and observe what materials get exchanged in this region. And so that Acrobat that I was talking about, as you can see here, is a towed research platform that you can attach a bunch of different auxiliary sensors to, depending on what your research goals are. And so we attach sensors to monitor chlorophyll A, temperature, salinity, density, dissolved oxygen, and turbidity. And here's a picture of me using it, my research colleague, Jesse, using it, and then Dave Wells here in the back using it as well. And this research would not have been possible without Dave. He did all of the real in-time troubleshooting that took place with the Acrobat, making sure all the sensors are calibrated. And so big shout out to Dave, because it would not have been possible without him. And what's cool about the Acrobat is it's a winged configuration, allows it to oscillate up and down in the water column as you tow it behind your boat. And so using this configuration, we ran 7 transects as depicted here by these red lines. And when you're towing something in the water for as long as we were, which was about 5 hours, inevitably you're probably going to catch something. And we did pick up a cannonball jelly throughout this time, but afterwards we tossed him back in the ocean and we're pretty sure he was just okay. So, and then after our in-situ data collection, we went back and looked at all of the satellite imagers that were looking at this region at the same time that we were taking our in-situ measurements. And that's depicted here by this dotted line satellite grid. And so we're going to zoom in on one of those pixels and see, we're going to collect our in-situ or our satellite measurements here up at the top, and the oscillating path of the Acrobat, which depicts where we took our in-situ measurements, took place underneath, whichever arbitrary pixel that you're looking at. And so we aggregated all of these in-situ measurements, and we calculated the mean of all of them. So we were able to have an in-situ measurement for every satellite pixel measurement. And we did that for the top 10 meters of the water column, because this is where we took the in-situ measurements. And then we chopped it up into 3 different depth intervals to see how well the satellite imagery was matching up with different depth intervals of chlorophyll A. And so on the day that we took our in-situ sampling on May 5th, this is what it looked like. It was a beautiful day, but if you've ever done satellite work before, you know that cloud coverage is not your best friend. So this is what the satellite imagery was looking like from the Hawkeye on this particular day. And if you really squint your eyes, you can see the RV Cape Fear right there. So unfortunately, all of the satellite imagery was not able to be used in the analysis. So instead, we expanded our acceptable window of satellite acquisition to 48 hours. So we took our in-situ measurements here, straddling that rising tide to a falling tide on May 5th from about 10 a.m. to 3 p.m. And then 48 hours later, we collected the satellite imagery from 4 different sensors: the Seahawk Hawkeye, Sentinel-3A, Sentinel-3B Ulchi, which are 2 sister satellites that kind of work in tandem with each other, and then Modus Aqua. But I'll talk a little bit more about those satellite sensors in the future. And here are just kind of some environmental characteristics of this region. This is a 24-hour change of chlorophyll A concentration at the mouth of the Mason-Burrow Inlet. This is from May 5th to May 6th. And as we can see here, you can have swings of 3 micrograms per liter of chlorophyll, and at any given location here, where it kind of looks like it increases at the mouth of the Mason-Burrow Inlet as that plume is coming out, and it decreases further from shore here. So it's a quite variable location, and it's also variable in wind vectors as well. On the day that we took our in-situ measurements on May 5th, we weren't really receiving much wind in the area, about 1 meter per second, and then it ramped up throughout the next couple days. And on May 5th, it was peaking with gusts of 9.5 meters per second, but on average about 5 to 6 meters per second. So this was probably creating some surface water mixing and probably some white capping going on in the ocean, which can also interfere with your satellite signals. So I'm kind of saying all this to say that this is just a really dynamic region. And by expanding this window from, what could have been a perfectly synchronized data set to a 48-hour window period between this, we're baking in a lot of variability between our 2 data sources. But with that being said, I'd like to show you a couple observations that we were able to, observe by running our transects. And so I'm going to show you 4 different parameters. Sorry, and I'm going to explain this plot real quick because it's kind of a lot to look at. But I'm going to show you 7 different transects of chlorophyll A in this case, but I'm going to show you 4 in the future. Going to be set up the exact same way. And they're all oriented in this kind of fashion here. So this is transect 1, which is closest to the mouth, and they're going to extend distance from shore here. And then distance across the transect. This side is set up so it's matches up with this part of the transect, and then vice versa here. And then in terms of depth, this is the shallowest region of the water column, and then this is the depth, the deepest, goes down to about 10 meters. And so this is chlorophyll. And so these were the trends that we observed. That oscillating pattern of the acrobat, we took all those measurements and then we literally interpolated them. So that way we had a nice pie slice for each of the transects to have a nice visual representation. And so we saw a increase from transect 1 to transect 7. And then we also saw an increase with depth. So this plot here on the left shows different depth intervals of chlorophyll A concentration. And so transect 1, transect 2, and so on. And then chlorophyll A concentration increases up the y-axis. And then there are 5 different depth intervals, each of which are 2 meters deep in the water column. And so the purple matches up with the shallowest region, and then the lime green matches up with the deepest region of 8 to 10 meters. And so as you can see, it kind of incrementally increases as you get deeper into the water column for each one of those transects. And this could be possibly due to the fact that as you get further from shore, water clarity probably tends to increase and the light is able to penetrate a little bit deeper in the water column. So you might be seeing some more primary productivity taking place at deeper depths in the water column. And it could also be due to the fact, it could be a result of non-photochemical quenching, which is when algae gets too bombarded with light and the chlorophyll, instead of fluorescing, it will offload all of that light energy as heat. So it's not going to convert any of it to chemical energy. And so if that were the case, we wouldn't be able to measure the chlorophyll A in that part of the water column. And that's usually more of a shallow water effect where light's intensity is at its strongest. And so here is temperature, set up the exact same way. Here are the trends that we observed throughout those 7 transects. We also saw an increase here as we moved seaward in terms of, or for temperature, about a 0.07 degrees Celsius change overall. And then we saw a decrease with depth. And what likely, it's important to note that all of these in-situ measurements were not taken all at the same time, simultaneously. They were taken across a 5-hour window from 10 a.m. to 3 p.m. So the first couple of transects were taken, 10 to 11 a.m. And the last couple were taken from 2 to 3 p.m. And so the sun probably got a little bit higher in the sky, as it does, and warmed the surface water. And so that's probably why we're seeing more of a stark change in the temperature in between the different depth intervals there, where the warmer water is more so concentrated at the surface and the deeper waters are a little bit cooler. And in terms of salinity, here are those 7 transects that we ran. We saw a very modest seaward decrease in salinity, just 0.02 practical salinity units. And then we saw an even more modest increase with depth of just 0.01 practical salinity units. And this is likely due to the fact that this is just a really well-mixed region. We happen to catch it at the time of a changing tide from rising to falling. So you have just a really dynamic region that it's not all that surprising that in terms of salinity, this is a pretty homogeneous water column. And then last but not least, we have density here. Where we saw a decrease when we moved seaward in terms of density. And then we saw an increase with depth. And this is, okay, so here we go. We ran a buoyancy frequency squared test, which quantifies the stability of the water column, giving stable portions of the water column a positive value and giving unstable portions of the water column a negative value. This plot here shows that it's basically like you're taking a side view of all of these transects. So you have 1 to 7, then you have the distance from shore here. And then in terms of depths, shallowest region up top, deepest region down below. And for the most part, we see a pretty, we see a water column that's pretty much in equilibrium. All of these values are kind of centered around that 0 point. You do see some interspersed positive values and negative values here, but judging from the data that we saw from temperature and salinity, both of which play into the density of the water column. It's not all that surprising that those modest changes in those two parameters resulted in just a water column pretty much at equilibrium. And so kind of shifting our attention away from in situ measurements and moving on to satellite imagery. Like I said, these images were taken 48 hours later on May 7th, and we collected samples or satellite imagery from Aquamotus, Seahawk Hawkeye, Sentinel-3A, and Sentinel-3B Ulchi. And we saw pretty significant differences in chlorophyll A concentration for each one of those satellites in terms of magnitude and in terms of range. And so here's what that looks like when plotted. We're seeing Motus up here at the top with the coarsest resolution of 1,000 meters per pixel. And then Hawkeye over here with 120, which was the highest that we observed. And then Sentinel-3A and Sentinel-3B Ulchi both had the same spatial resolution. Those red lines just indicate where we ran our transects, just to kind of give you some spatial context there. And one thing to note about the spatial resolution of a satellite imager, when you're doing this type of science in a coastal region, kind of hearkening back to the types of interferences that can occur, you can run into some shallow bottom effects, as well as some adjacent landmass reflection. And so that means that some of these pixels that are closest to shore are going to get flagged and removed from the plotting of your data during the processing of the satellite imagery. Which means if you have a big pixel and just a teeny bit of that corner gets flagged, well, then the whole thing gets removed from the study. So you're going to miss a lot of data when you're working with a coarser satellite imager rather than a high resolution imager, which you can pack some more pixels in there before they start to become interfered with. So when we look at the distribution of the chlorophyll A concentrations that we observed in each sensor, we saw a kind of similar pattern emerge where the Hawkeye had the most symmetrical normalized distribution of chlorophyll A counts. And the other three kind of followed the same trend, but they were a little bit more right skewed here, where you had some higher order magnitude of chlorophyll A concentration skewing those results. But when we replotted the satellite images based on each one of their specific ranges, we saw similar patterns of spatial distribution of chlorophyll emerge, where the highest concentration of chlorophyll A was closest to shore, and then it kind of tended to drop off as you got a little bit further from shore. So there's maybe some nutrient wafting off of the nutrients wafting off of the shore there, causing primary productivity to take place. And then another satellite parameter that we were looking at was KD490. KD490 is the diffuse attenuation coefficient of light at the 490th nanometer of wavelength. And it describes the rate at which light diminishes as it passes through the water column. And so a low KD490 measurement would indicate clearer waters, deeper light penetration, as seen here on the left. This is more so characteristic of like the open ocean when you have less suspended sediment in your water column. But when you have a high KD490 measurement, it would indicate a turbid water ecosystem where you have numerous light or particles in the water scattering light. This is more so characteristic of the coastal water body like we see here in Wilmington, offshore. And so since KD490 is measured in inverse meters, you can take per meter, you can take the inverse of this and find the first optical depth, which is a helpful metric for determining the euphotic zone and where light is sufficiently available for primary productivity to take place. And so when we sampled our satellite imagery targeting the KD490 measurements, we saw similar trends with what we did with chlorophyll A. We just saw different magnitudes exist between all of these satellite imagers. So the Hawkeye showed the lowest KD490 measurement, as seen by that deep purple hue here, which would indicate the deepest first optical depth. And then Sentinel-3B Ulchi had the highest KD490, which would indicate the most shallow optical depth. When we plotted the KD490 based on the specific ranges like we did with chlorophyll, we saw pretty similar trends with KD490 exist, where you had the lowest KD490 scores at the shallowest point or at the point that's closest to shore, where it's a lot more shallower and where you probably have a lot more suspended sediment content in the water column, creating a turbid environment. And then it tends to clear up as you get a little bit further from shore there. And then after running our water quality evaluation, we did a matchup analysis. And this is when we subsetted our satellite imagery to just include measurements that were perfectly coincident with our in-situ transects. So it kind of reduced our data points that were available. And then we included the Acrobat data here. And then we used 4 statistical metrics to quantify any sort of discrepancies that existed. The first of which was an R-squared metric, which shows the goodness of fit between 2 data sources. So a good R-squared would be a 1, and that would be perfect alignment there. And then a bad one, a really bad one, would be a 0. And then it exists kind of on a spectrum between those 2 points. And then we use bias here to describe if a satellite sensor was continuously overestimating or underestimating our in-situ points. Overestimation would mean that it would give us a positive value, and then an underestimation would give us a negative. And then 2 error metrics we used was root mean squared error and mean absolute percent error, as seen there at the bottom. And these 2 metrics quantify any sort of errors that exist between our 2 data sets. And they give a score. RMSE gives a score in an integer form. A high integer would indicate lots of errors exist between the two data sources. And then MAPE gives one in a percentage. A high percentage means that a lot of errors exist. So we ran our linear regression test on the Hawkeye image first. This incorporates a 0 to 10 meter portion of the water column, so all of our in-situ measurements. We have our in-situ chlorophyllite concentrations here on the x-axis and the satellite-derived measurements from Hawkeye here on the y-axis. And then because there were so many data points available, a whole whopping just under 10,000, we included a color bar to show where these points were most densely packed in. And then that orange line there shows the line of best fit for the 2 data sources. A perfect line of best fit would be a nice 1-to-1 diagonal line there, which we're not seeing in this case, which indicates a poor fit between these 2 data sets. And then we ran it on the remainder of the measurements. There we go. So we have our 3 other satellite sensors here, all of which were done in the entire water column of in-situ measurements. We're kind of seeing the same trend emerge from each one of those, where we're really just not having a great line of best fit as seen here to indicate that these 2 data sources are in good agreement with each other. And then, like I said, we chopped it up into those different depth intervals. We did see a spike here in terms of nice diagonal line there for the topmost portion of the water column for MODIS. However, data points are quite sparse here. We really only had 16 to work with. So this is likely probably just a coincidence rather than like an indicator of anything significant in terms of these 2 data sources. And then with the intermediate value, or with the intermediate depth range of 4 to 7 meters, kind of saw a lot of the same thing. And then finally with the deepest portion of the water column, we saw the same thing continue. And in terms of our statistical metrics that we use to quantify any discrepancies, the R-squared one, we saw a universally low score, aside from that one spike that we saw in the shallow region for MODIS. The bias showed that Hawkeye was consistently underestimating our in-situ measurements, while the other satellite sensors were overestimating to varying degrees. And then the 2 error metrics showed that Hawkeye had the lowest amount of errors, and the other sensors had a little bit higher, with Sentinel-3B having the highest error rates amongst its matchups with the in-situ data points. So it's safe to say that these 2 data sources just were not seeing the same thing on the 2 days. And so to return back to those initial research questions, how can the integration of our in-situ and satellite-derived measurements enhance our understanding of the water quality parameters in the Cape Fear River? Well, by using satellite imagery, we were able to use a cost-effective approach to collect imagery and data points to work with. When we did have that unfortunate weather, kind of hiccup in our data collection method on those in-situ sampling on May 5th, we were able to just kind of switch gears and just look at satellite imagery on May 7th, with just a couple of extra clicks on the keyboard and clicks of the mouse. It wasn't all that complicated. And with the in-situ measurements, this provided the highest resolution of imagery. We were able to collect 83,000 data points here, and we got to see some nice characteristics inside the water column, but it just required more resources. So we had to coordinate with a crew and reserve the RV Cape Fear, which was done months in advance. And unfortunately, we weren't just able to say, we can't do it today, when we got out there. And plus, when you're on the deck of the boat, it's hard to say, is this cloud coverage enough to, render our satellite imagery useless? It's kind of hard to know that cutoff point with your naked eye. And so by collecting our in-situ points with our satellite imagery, we were able to collect some ground truth data to improve some of those empirical algorithms like the OC4 algorithm, as well as some of my analytical models that are used for estimating chlorophyll A concentration. And then by using the satellite imagery, we're able to get nice broad snapshots of what the water column was doing in this region on May 7th. And then by integrating it with in-situ measurements, we were able to provide nice continuous three-dimensional perspective of the water column at different, in terms of different parameters of the different constituents in the water column. And then by integrating these two data sets, we were able to observe that the KD490 in the satellite imagery decreased as you got further from shore, which would indicate that light was penetrating a little bit deeper in the water column. And then when we looked at our chlorophyll concentration in the in-situ measurements, what were going on in the water column, we saw that the chlorophyll A concentration was indeed picking up as you got a little bit deeper there. So that was a nice observation we saw by using this integrative approach. And then how do specific satellite sensors perform in observing physical and biological parameters in coastal regions? Well, we assessed 4 of them, and we saw very significant degrees in terms of variability and spatial resolution. And this kind of affected our data analysis, where we had the most data points to work with Hawkeye because it provided the most data points and highest spatial resolution. And it also included some data points that were missed by the other satellite sensors because we got a little bit closer to shore there. But in terms of chlorophyll A concentration, we saw a high degree of variability in terms of magnitude, even though Hawkeye showed the lowest and Sentinel-3B Ulchi showed the highest, even though that these two images were taken just 15 minutes apart. But the spatial trend was consistent between all 4 of the satellite sensors, where we saw the highest chlorophyll A at the shore, and then it decreased as you got further from the shore. And then what discrepancies exist between the chlorophyll A concentrations? Well, we saw in terms of chlorophyll, a lot of discrepancies exist between the satellite sensors themselves, as well as the satellite sensors versus the in-situ measurements. And this was confirmed with our statistical metrics that showed that we had poor model fit, as well as high error rates between all the different combinations there. And so what could be contributing to these discrepancies? Well, spectral resolution could be a start where different satellite sensors are imaging different portions of the electromagnetic spectrum just slightly. And so this can affect your algorithm application, where take OC4, for example, where that uses a specific wavelength band ratio. So if your sensors are collecting measurements from different wavelengths, then that's going to affect the overall output of what your chlorophyll A estimation is going to be when using an empirical algorithm like that. And then the wavelengths also are used for conducting atmospheric correction, where if you have different wavelengths being measured by different sensors, this can affect the overall effectiveness of your atmospheric correction. And also different sensors utilize different methods for doing atmospheric correction, where some sensors can tilt to avoid sun glint, kind of like the Hawkeye, and other sensors can't, like MODIS. So it has to remove sun glint from its top of atmosphere received signal by using a more mathematical approach. And this could introduce some variability there. And then sensors with a high signal to noise ratio can distinguish the signal that you're trying to make out in your satellite signal amongst all the noise a lot better. And so some sensors have a low signal to noise ratio, or SNR, especially in coastal ecosystems, because there's just a lot of optically complex particles in your water column that are affecting the scattering and the absorption qualities of light. And so some of these constituents are You have a lot more color dissolved organic matter here. You have particularly high suspended sediment here, and you can have a lot more wave action here and things like that that can throw off your that can cause you to have some difficulty distinguishing that chlorophyll A spectral signature amongst all the other spectral signatures you're picking up in the water column. And also depth of measurement was different amongst our sensors, which were our satellite sensors, which were imaging some portion of the shallowest part of the water column, and our in-situ measurements were taken, in the 0 to 10 range of the water column. And then probably one of the highest or most likely contributing factors was that our satellite imagery was taken 48 hours after our in-situ measurement. Unfortunately, we would like to have perfectly synchronized data sources, but it just did not work out in this case. And so by integrating these two data sets, in conclusion, we were able to have a more complete understanding of the biophysical and biogeochemical interactions within this region. We're able to understand light's penetration effects on photoplankton dynamics a little bit better, and we're able to detect and track a phytoplankton plume, both broad level on the surface water as well as in depth in the water column. And when we ran our analysis between our matchup analysis, we saw some pretty significant discrepancies. And we hypothesized some contributing factors that could be affecting this. And we also, this kind of led us to the conclusion that continued characterization of these satellite sensors and pigment algorithms are required for comparable results across sensors in these coastal regions. And so our future research directions, we would say that these should prioritize ongoing validation efforts to enhance satellite-derived measurement models through continued ground truthing data collection. And so I'd just like to acknowledge a few folks that this research would not have been possible without. So thank you to my committee, Dr. Bresnahan, Dr. Liu, and Dr. Halls. Thank you to the Gordon and Betty Moore Foundation for the financial support. Dr. Bruin and my fellow Coast Labbers, I appreciate all the help there. Dave Wells and Bruce Monger, who helped with the technical skills like data collection and satellite image processing and all the fieldwork stuff. And then thanks to my family, my run club friends, and my dog park friends who provided moral and emotional support during my studies. So thanks, guys. References? And any questions?
Thanks, Mitch. So we have time for questions from the audience. I'll keep an eye on Zoom too, if anyone has questions in Zoom. Go ahead. Yes.
What would you consider the most challenging part of this process, and what did you learn from it?
Well, I'd probably say the hardest part was doing all this, the imagery, processing and analysis from the satellites. And taking that course at Cornell actually really helped with that, because Bruce was an expert with this kind of thing. And he was really closely involved with all of the people that worked at NASA and things like that. So he could talk to us about different satellite missions and why certain ones came about. And he helped us work with Python and showed us the ropes with that on how to process imagery in kind of large batches. So that was really helpful. Yep.
I don't have an answer for this, and I don't know if anybody does, but do you think that there would be better like in situ and satellite matchup in different areas? Because I know like it wasn't great in the Cape Fear region. Do you think it'd be better in different areas?
I mean, potentially for sure. I think in terms, it wasn't great here because we just didn't have the right alignment time-wise, but yeah, I would say that if the satellite imagers were, as accurate as they say they are, which not always is the case, and then our in-situ measurements are, in any general coastal region, they should match up pretty strongly, you would think. But definitely future research needs to be done on that. And there's a lot of studies that do similar things that we've done with the matchup analysis that have had particularly better results than we did. Yep.
What was your favorite part of your project?
Probably taking the boat out. Riding on the RV Cape Fear was a lot of fun. We saw dolphins on May 5th, which was really cool in the intercoastal waterway there. And yeah, just seeing how all that works and taking the acrobat out and seeing all the cannonball jellies. We saw a ton of cannonball jellies from the deck there. I mean, hundreds. So, yeah, that was a fun day. Yep.
Is there only one Hawkeye in space right now?
It is in space right now. It's unfortunately decommissioned, so we
Oh.
can't get data from it anymore. But the overall, it was a proof of concept mission to see if high resolution imagery could be captured by using a low cost sensor. And so, if the mission is deemed a success, there's a potential possibility for launching like a constellation of Hawkeyes, which would improve like the temporal resolution of it. It could only come back to the same place on Earth at its best, like every 14 days. And so if you had a couple of them going all at once, you could bring that down and get more measurements.
When will they know if it's deemed a success?
That's a good question. I don't know
Okay.
personally.
Was it deemed a success? Is that the?
When will they know if it's
When
deemed
will
a
they know?
success? Yeah,
When will who know?
I guess.
Whoever's supposed to deem it a success.
When there are multiple successful master's thesis defenses and publications that
Okay.
arise from the work.
Okay, awesome.
Yeah.
I have a question of like, whether it's just like, I guess it being on the coast in such a dynamic ecosystem, if those satellites could be, like, were they built better for maybe more like open ocean and like large regions that aren't as dynamic, I
Sure.
guess, even though I guess the open ocean also can be dynamic.
Yeah,
well, you
no,
know, as
absolutely.
much.
That's a good question. Yeah, the Modus Aqua is particularly it comes to mind as one of the more open ocean since it's like more geared towards that. It's kind of coarse pixel resolution kind of mirrors that because it can cover such a huge part of the planet in a rapid time. It comes back to the same spot on Earth every 2 days. So yeah, it's more so geared for assessing kind of like a quick and dirty assessment of the whole globe pretty rapidly. So
Cool.
yeah.
Questions? Let's thank Mitch again.
Thanks for coming out, everybody.
Excuse the general audience and ask the committee to stay, please. You had some comments in the chat on Zoom. That's a nice job as well.
Thank you. Thank you, Sam.
And this
Here.
Great job, Mitch.
I appreciate it.